In this lesson, we will discuss the diode model, and the model I am referring to now is what is known as the large signal model. This simply refers to the fact that we are dealing with total quantities, that is the total voltage across the diode and the total current in the diode, and not incremental values over certain operating point. Okay. This is the diode symbol, and we have the anode and cathode. By convention, I will define the voltage across the diode to be positive at the anode terminal. Value of Vd of course can be anything, and the current Id will be flowing into the anode as per passive sign convention. Now, we already have seen a model for this. The diode current is Is times exponential diode voltage by thermal voltage minus 1, where Is is the reverse saturation current, and Vt, which is Kt by Q, is the thermal voltage. And if you substitute the values for 300 Kelvin or room temperature, this is approximately 25 millivolts. Okay. And we also know what the characteristic looks like graphically. The currents can be substantial when Vd is positive, and it will saturate to minus Is when Vd is negative. Okay. And of course, the current is 0 when the diode voltage is 0. Okay. Now, even with this expression for the diode current, and even for very simple circuits, evaluation becomes very difficult because you have to solve equations numerically. Okay. So, we have a number of approximations to this, which I am going to discuss now. So, one of the first things to do, sometimes this is very convenient, is to neglect this 1 when compared to this, and of course, this works only when this term is very large. And when is it very large? When Vd is large and positive. When I say large and positive, Vd must be much more than the thermal voltage. Okay. In this case, clearly the exponential of this is much more than this. Okay. For a Vd of a few thermal voltages, this turns out to be correct, right. So, a couple of 100 millivolts is all we need, and in this case the diode current can be approximated to be Is exponential Vd by Vt. Of course, it must be remembered that this holds only when Vd is much more than the thermal voltage. Okay. Now, if you do plot this, what happens is, in this region where the current is substantial, you will get approximately the same value. One crucial difference between the exact expression and this is that our new expression does not go to 0 when Vd equals 0. Okay. So, this means that if you plot this characteristic, there will be a part in the second quadrant, which means that the device is not passive. Of course, the reality is that near the origin, near Vd equal to 0, this expression should not even be used. It is only an approximation. Okay. And another approximation frequently used is that because the reverse bias current is so small, this value of Is is quite small, and again when I say small compared to currents you normally see in forward bias. Okay. Then you assume that there is no current flowing through the diode, that is, in reverse bias there is no current in the diode. This is one of the approximations that is frequently used. Of course, we are still left with a nonlinear equation, and this is useful for certain classes of circuits but still even for simple arbitrary circuits you have to solve nonlinear equations, okay, and we would like to avoid that for hand calculations. So, the next approximation that you see is that if you look at this part of the curve is quite steep. I am plotting ID versus VD and the curve is very steep, okay. So, what you can say is that in this part of the curve the diode voltage does not change much, okay. It of course changes. In fact, I will use this approximate expression to find the expression for the diode voltage. So, VD will be the thermal voltage times the natural logarithm of the diode current by the saturation current, okay. So, now let us say ID is doubled, ID becomes 2 ID, then this changes to VT ln 2 ID by IS, which is basically the old value VT ln ID by IS plus VT times the natural logarithm of 2, okay. And if you calculate this, it will come out to be approximately 17.5 millivolts. So, even doubling the current changes the diode voltage only by something less than 20 millivolts, okay. So, we can make a reasonable approximation that for a range of currents the diode voltage is constant. That is, we assume the characteristic to be exactly vertical, where the diode voltage is not changing at all. Of course, this gives you very bad errors when you come close to the origin, but that is okay. We assume that the diode is operating somewhere here, okay. So, we say essentially the next level of approximation is to say that the diode voltage is a constant when there is some current flowing in the forward direction, okay. Okay. And also we know that the current is very small in the reverse bias region, and we already approximated that to 0 earlier, okay. That is, we assumed a characteristic of this type, and we can continue that all the way till here, okay. So, we assume that there is 0 current up to this point, and at this point the voltage will be constant and it can carry any current, okay. So, the next level of approximation is as follows: forward bias, which means that substantial ID flowing, of course, in the forward direction. In the reverse direction, substantial currents cannot flow in the diode at all. So, in this case, what happens? Vd is some constant which is denoted by Vd on. And what is the value of this constant? Essentially, the way you work out this constant value is you have certain types of diodes that you normally use, and you have certain range of currents that you normally operate at, and for that you just look for a reasonable value, and it turns out that a reasonable value for this is 0.7 volts. Okay. Now, this does not have to be the case. If you operate diodes with very small currents, it could be smaller than this, and also in diodes which carry very large currents, it could be more than this, even as much as 1 volt, but we will assume that it is 0.7 volts. Okay. But the important thing is that it is assumed to be a constant regardless of the value of current. And then I will call it reverse bias. Basically, when the diode is off, by the way, I refer to this as the diode being off, and I should not really call this reverse bias because Vd is not necessarily negative, it also includes Vd less than 0.7 volts. So, this means that if Vd is less than 0.7 volts, this means the current will be 0. Okay. So, if Vd is less than Vd on, the current will be 0. The forward bias is when the diode is on. So, it looks like some kind of a switch where it can go from off state where there is no current to on state where the voltage is constant and it can support any current. Okay. Now, this is fine. This is in fact what we will use for our large signal calculations. Okay. And there will be some cases where we can approximate this even further. Let us say we have circuits where the voltages are much larger than 0.7 volts, and it turns out that you can approximate this as having 0 current when Vd is negative and having a 0 voltage when there is any current flowing through it. That is, we even make a cruder approximation of Vd on. We make an even cruder approximation for Vd on by setting it to 0 volts. Okay. That is, the diode behaves like a short circuit when there is a positive current flowing, and the diode behaves like an open circuit when a reverse voltage is applied. Okay. If you remember, I versus V of a short circuit is as follows. It is this, it will have 0 voltage regardless of the current that is flowing, and the IV characteristic of an open circuit, it is like that. It will have 0 current regardless of the voltage across it. Now, the diode is a combination of these two. It is an open circuit in this part in reverse bias region and a short circuit in the forward bias region. So, that is another approximation to the diode characteristics. Okay. So, to summarize, we have the exact characteristics of the diode, and this exact I will put in quotes because this is still an idealized version of the diode characteristics, and in a practical diode you will have other non-ideal features. But as far as we are concerned, this is the exact characteristic. And this is valid for all values of Vd. And then we have the first level of approximation where we say that Id is just the exponential without this -1 term when Vd is much more than Vt, and it is 0 when Vd is less than 0. And we have a second level of approximation where we say that if there is current flowing through the diode at all, forward current flowing through the diode, then the diode voltage is some constant Vd on, which we will take as 0.7 volts, and if the voltage happens to be less than Vd on, then the Id will be exactly equal to 0, and in this model the diode voltage cannot be more than Vd on. Okay. And an even cruder version of this is to say that if Id is more than 0, Vd is 0, and if Vd is less than 0, Id equals 0. Okay. So, this is the on diode and that is the off diode. Okay. In this course and generally in many courses for hand calculations, you will end up using this as a reasonable approximation. Okay.